Yeah, maybe you can start. So it's really a pleasure to have Juntao from Texas, and he will be talking about the radiative transfer equation. So please, Juntao.
Okay. So first, I would like to thank Professor Masmoli for the kind invitation. And today, my topic will be we want to do some reduced model for the radiative transfer equations. So here we are trying to use the machine learning as a tool to help us to derive some reduced model. And here we want to preserve some stability of the reduced model. So that's our focus today. And this is a joint work with Professor Inda Chen and Andrew Christie in Michigan State University, Luke Roberts in Los Alamos National Lab, and Wen Anyong in Tsinghua University in China. Okay, so first let me show you my background. The background. Well, I believe you are very familiar with the kinetic equations. So the kinetic equation is trying to describe a large particle system using a distribution function f. So here the unknown function f is a function depending on x, v, and t is trying to describe the particle densities with the traveling velocity v in the velocity space. R3 typically, and x is the position in the physical space and t is the time. So in the multi-scale modeling, the kinetic equation, the scale stands between the continuum mechanics, for example, the Navier-Stokes equations you are very familiar with, and the Newtonian mechanics for the particle. Okay. And it has wide applications in many different fields. For example, the real-field gas dynamics, that is the so-called Boltzmann equation. And in the plasma physics simulation, people have to solve the Vlasov-Maxwell equation. And here we are focusing on the radiative transfer equation, which has been widely used in the nuclear engineering and astrophysics. All right. And this figure shows the problem of two neutron star merger along with the resulting gravitational waves. And to simulate this problem, people also have to solve the so-called radiative transfer equation. But numerically, there are two essential difficulties if we want to solve the kinetic model. The first difficulty is the multi-scale feature in both space and in time. But we will not focus on this issue today. The main focus of today in today's talk is the so-called high dimension for the kinetic model. So if we consider the real-world problem in the 3D, and then the total dimension of the phase space for the distribution function would be 7. That is 7 dimension in the physical space, 7 dimension in the velocity space, and 1 dimension for the time. So if you want to apply the standard mesh-based numerical scheme, such as the Phelan difference or Phelan element method, then you would have the so-called curse of dimensionality, which means that the computational cost will increase exponentially with respect to the dimension. Okay, that's the difficulty numerically. So this is the formulation of the radiative transfer equation. The left-hand side of the RTE describes the propagation of the radiation, and the right-hand side, it describes the interaction with the background medium. So here F is the so-called specific intensity of radiation in physics. It depends on X that is the location in the physical space. Omega, that is the unit sphere in the d-dimensional space, which means the travel interaction in the angular space. And on the right-hand side, it involves some integral of the distribution function over the angular space. And sigma s and sigma t are some given positive functions denoting the scattering and absorption of the material. So here we are trying to derive some reduced model for this high dimensional PDE. That's our focus today. So we are trying to use the so-called moment closure method to derive the reduced model. This method is first introduced by Graz in 1949 for the Boltzmann equation. And mathematically, it is essentially some dimension reduction technique. So it's trying to reduce the dimension of the original equation from 3D in the physical space plus 2D in the velocity space, or the so-called angular space, to only 3D in the physical space. So it's trying to derive a model which only depending on x in the physical space and get rid of the angular space. All right, and physically, it's focused on the evolution of the moments of the specific intensity. So the moments here, I mean, if you compute the integral of f over the whole angular space, then that is the so-called zeroth order moment, which means the energy density in the physics. And the first order moment is the radiation flux, and the second order moment, that's the radiation pressure. Okay, so to show you what is the moment closure problem, let me make this simplified model. So that is the RTE in the 1D for x and 1D for the velocity. And in this simplified case, that the RTE will be simplified to this formulation. The left-hand side still describes the propagation of the radiation, and the right-hand side describes the interaction with the background medium. All right, so to derive the moment model, we first introduce the definition of the moment. MK, that is the case of the moment. It is a function depending on x and t. It's defined by the integral of f multiplied by some Legendre polynomial of the velocity over the whole velocity space from -1 to 1. And by multiply this original kinetic equation with some basis function in the velocity space, we can easily derive this the so-called moment equation. For example, the first equation, that is the evolution equation for the zero moment, it can be obtained from the directly integral this equation from -1 to 1 in the velocity space. Then the first term will become the time derivative of m0, and the second term will be the spatial derivative of m1, and the right-hand side will be depending on m0. And generally, the time evolution of the nth order moment will depending on the spatial derivative of the next higher order moment, mn plus 1. So if you want to solve this model numerically, then you would have to truncate it and introduce some closure relation. So the closure relation can be as simple as just remove this term, remove this higher order moment. Then you would obtain a hyperbolic equation with the constant coefficient. That is the so-called PN closure, which is very popular closure method. But this closure method may not be very accurate because you are just throwing away this high order moment. And then people came up with a lot of different ideas to close this method. And this MN closure is trying to solve an optimization problem, which trying to optimize the so-called entropy for the RTE and obtain a closed relation. So I will not go into the details for this traditional closure method, but I want to mention that all these closure methods have to introduce some empirical assumptions. For example, you have to assume that this high order moment is small enough, then you can throw it away. But these empirical assumptions may not be true in all the regimes. Then computationally, this is not accurate. Okay. So this motivates the introduce of machine learning. And machine learning, I think it has been very popular, especially in the recent years. People use it to solve some multi-scale problems. For example, in the molecular dynamics, trying to learn the so-called potential. And in the turbulence community, people are trying to close the turbulence model. And people are also trying to solve the PDEs in the high dimensions directly using the neural network. But here we are trying to focus on the using the machine learning to do the closure for the kinetic model. So in this context, the pioneering work was introduced by the group of Wei Nanyi in Princeton in 2019. The main idea is that they are trying to learn this closure. So basically, they're trying to represent the next higher order moment in terms of the a function depending on the lower order moment, and this function is represented by a neural network. And then they train the neural network with the data generated by the kinetic model. By doing such an approach, it is expected that the resulted machine learning moment closure will be accurate because it is trained with the data from the kinetic model. So it is accurate. It is an accurate approximation to the original kinetic model. All right, and then it has been generalized to some other models like the Williams-Boltzmann equation in this paper. And then in the plasma physics community, people are trying to learn some non-local closures for the Euler-Poisson system, and also the Hermite-Perskin closure for the Landau damping problem. All right, and there are also a lot of works here. But I want to mention that all these works cannot preserve the stability, except for these two papers here. They are trying to learn the surrogate maximum entropy closures. So our topic today here is that we want to construct some machine learning closure such that it has some provable stability. Okay, so
I actually have a question now. When you call it machine learning closure, like this Mn plus 1 equal n of, I mean, it's the same. I mean, it is also some empirical assumption that you put to calculate Mn plus 1 as a function of the previous moments, right?
Yeah. It still introduced some assumption, but I would say that that is some mild assumption than the traditional closure.
Okay.
Yeah, so that is some assumption, and actually, well, that's a very good point. I think so because there are some work, for example, in this paper, they are trying to assume that Mn plus 1 at some location x, depending on some lower the moment in its neighborhood. So they call it the non-local closure. That's another assumption. So this is actually trying to assume that the higher the moment depending locally on the lower the moment. Yes. All right. Okay. So so I want so in these slides I want to mention I want to introduce what is the stability. I mean, in this context. So here is the machine learning moment closure model when I replace the next higher order moment Mn plus 1 by this neural network depending on the lower moment. So this is actually a time-dependent first order partial differential equations. And here M is the vector include of M0, M1 up to Mn. And this is the time derivative, spatial derivative, and the source. So for this first order time dependent PDE, there is a very important concept named hyperbolicity. So we say that this system is hyperbolic if and only if this Jacobian matrix A is real diagonalizable. And this hyperbolicity is crucial for the long-time stability of the model, but the main difficulty is that because this neural network is essentially a black box, so this Jacobian matrix will depend on the derivative of the neural network. So generally, if you just put a black box neural network here, then you cannot ensure that this matrix is real diagonalizable. So that's the main difficulty of the machine learning closure to preserve the stability. All right. So in the next part, I will show our work of how to preserve the real diagonalizability of this Jacobian matrix. So that's essentially a linear algebra problem. Okay. So let me first show you my motivation. So to derive some closure relations, we first consider this simplified model. So we just get rid of the right-hand side. We say that it is that is the so-called free streaming limit in physics community. We consider this simplified model with the isotropic initial condition. This initial condition does not depend on the velocity. So for this simplified model, we can derive some closure or exact closure relation. And motivated by that exact closure relation, we propose to directly learn the gradient of the unclosed moment in such a formulation. So you can see that the gradient of the next higher order moment will depend on the gradient of the lower order moment. And the coefficient will be represented by some neural networks. So it is slightly different from this closure relation. Actually, this relation is in the conservative form, but our learning gradient relation is in the non-conservative form. All right. So why we want to use such a formulation is because first, it is more accurate.
I have a question.
Yeah, sure. Sure.
Okay. Now, when you write n of m0, m1, mn, I mean, you are thinking about it as a functional, right? It's not. It's not for each point x that you have that, right? So it's more like a functional, right? It's the whole function of m0, the whole function m1.
Actually, I'm writing this as a function, not a functional. So
as a function at each point x.
Yeah. At each point x, it satisfies some. I mean, locally, depending on the lower moment, not the whole function.
Okay. Okay. So it is okay. So then there is a difference between 7 and 8, right? So then
So actually, you can see here it is some function. So for example, so it's some function, then that is some partial differential equation. Otherwise, that's not a differential equation if this is a functional.
Okay. Yeah. That's what I was thinking. Yeah. So you want really to think about it as okay. Okay. But then, I mean, if you take 7 and you differentiated in x, you get 8. I mean, if you take 7, if you have 7 and you take a derivative in x, you get 8.
Yeah, sure. So
somehow 8 is more general than 7. That it's a relaxation of 7.
Yeah, this coefficient might not be some gradient of some scalar field.
Okay. Right. Okay. Yeah. Okay, I understand.
So thank you for the question. So all right. So here there are several advantages. First one is because the exact closure we have derived from this toy model has such a gradient formulation. So we expect that this ansatz will be more accurate in the so-called optically thin regime. So typically that's some physical word. It means that the system is far away from the equilibrium. Okay, and the second point is that it is easy to enforce some mathematical structure because we have more degrees of freedom. So here we have n+1 degrees of freedom. We have n+1 neural network here. So we have much more degrees of freedom to play with than the above relation, so that we can more easily enforce the hyperballistic and some other properties. That's the second point. And if we want to use the equation 7 as our ansatz or the neural network, then we don't have any good idea to enforce the hyperballistic. Yeah. All right, so under this framework, we propose two different approaches to enforce the hyperballistic of the model. So before I introduce the main idea, let me first write down the model in our gradient-based machine learning closure. So this is our model, and the M is the collection of the moments, M0, M1 up to Mn, and Am is the coefficient matrix. So here you can see that the only the last row of the matrix is involved with the neural network, right? Because we are only modify the last row or the last equation of the moment closure system, and the remaining equations are just some constant coefficient. All right. So then the question is, how can we enforce the degrees of freedom in the last row, these neural networks, such that this matrix is real diagonalizable? That's a linear algebra problem. All right. So we have two different approaches here. The first one we call the symmetrizer-based hyperbolic closure. So the main idea is that we are trying to seek a symmetrizer that is the SPD, a symmetric positive definite matrix A naught, such that this matrix left multiplied by the coefficient matrix is symmetric. So in this case, we say that the system is symmetrizable hyperbolic, and moreover, under this assumption, we can prove that the machine learning model will converge to the diffusion limit of the kinetic model as the Newton number goes to 0 in the diffusion limit. Okay. So starting from this idea, we can derive some constraints for the degrees of freedom in the last row of the matrix A. And this is looks very complicated, but the roughly speaking, it is that we can just take the AI to be 0 for I from 0, 1 up to n-4. So we are just take the first several entries in the matrix to be 0 and leave only last 4 entries, and the entries satisfy some inequalities, algebraic inequalities. Then we can show that there exists some SPD matrix symmetrizer such that this matrix A naught left multiplied by A is symmetric. That's the rough idea for the first approach. And the list two constraints can be enforced by some post-processing of the neural network. All right. And then we introduce our second approach. We call it the eigenvalue-based hyperbolic closure. So this idea is motivated by some algebraic structure of the matrix A. Actually, if we move back to these slides, then you can see that in the upper right diagonal, in the upper right part of the matrix, most of the entries are 0. So it is actually a lower Hansberg matrix. And for this matrix, we can easily write down the characteristic polynomial. So we can derive that the characteristic polynomial can be represented in terms of the Legendre polynomial. And the coefficient of the Legendre polynomial will be related to the degrees of freedom in the last row of the matrix. That's our conclusion. And starting from these mathematical results, we propose to approximate the eigenvalue by using a neural network. So this is our neural network architecture. So the step one is to represent the eigenvalue. So eigenvalue is denoted by z0, z1 up to zn here. It is some function depending on m0, m1 up to mn. This function is represented by some formally connected neural network. And after that, the eigenvalue is processed by some hyperbolic tangent function, which is trying to enforce that the eigenvalues are in the range of -1 to 1. Because in the original RTE, the traveling speed is also between -1 to 1, or physically speaking, it is limited by the speed of light in the radiative transfer equation. All right, that is our eigenvalue. Then after that, it will be fit into the Virta's formula, trying to transform the eigenvalue to the coefficient of the polynomial. And then we have a linear transformation, transform the coefficient of the monomial basis to the coefficient of the Legendre polynomial. Then that is the degrees of freedom in the coefficient matrix. All right, that is the idea of our second approach. Okay, then let me show you some numerical results. So here, because we want to train our machine learning model, so we have to generate some training data first. To generate the training data, here we have to numerically solve the radiative transfer equations. Here we use the use some standard numerical method, the space-time discontinuous Galerkin method. And this is our numerical setup. We use the unit interval in the physical space with the periodic boundary condition. And for the initial condition, we use some truncated Fourier series up to some frequency 10 in the physical domain. And the coefficient will be randomly sampled from some given interval. Okay. And sigma s, that is the scattering, and sigma a is the absorption coefficient, are randomly sampled in some given intervals, and is taken to be a constant over the whole physical domain. And we take 100 different initial data. For each initial data, we use the DG method to evolve up to some final time 1. And this is our setup to generate the training data. All right. And after we generate the training data, then we can train the machine learning model. After we have a well-trained machine learning model, then we can use the machine learning model to predict some standard benchmark test in the RTE community. So the benchmark test I presented here is the so-called two material problem. So I want to point out that this two material problem is not in the training data. So so this shows the this is one we want to test the so-called generalizability of the machine learning model. Okay, so here we show some results. This is the profile of the zeroth order moment at time 0.5. And this x-axis denotes the physical domain, and the y-axis is the value of m0. That is the zeroth order moment. And in the middle part of the domain, that is in the gray color, it's in the optically thin regime. So in this regime, the system is far away from the equilibrium. And in the other parts, near the boundary, it is in the, we take sigma s to be relatively large such that it is in the intermediate regime. So the system is closer to the equilibrium. All right. So here we compare our hyperbolic closure, hyperbolic machine learning closure, and the non-hyperbolic machine learning closure, and also the traditional PN closure method. So here we take 6 moments, and we can see that both hyperbolic and non-hyperbolic machine learning closures agrees quite well with the exact solution generated from the kinetic model. But the PN closure, that is the traditional closure, has large deviations in the middle part because the system is far away from the equilibrium. So it's more difficult to generate a good closure method in the middle part. Okay. And this is at the short time prediction. And if we involve,
what you call,
yeah,
that question, what you call PN closure is like by like by minimizing entropy or something like that. What do you mean by PN closure?
Yeah, so the PN closure is simply remove the next higher order moment. So you take the next higher order moment to be 0. Yeah. So they assume that
but
that is sufficiently small. Right.
No, but I thought usually like the closure will be for instance to say to minimize the entropy or something like that. That's how
that's the so-called maximum entropy closure. That's that's called the MN closure.
Yeah, but I think you should be more comparing your result to that closure than this PN1 because it seemed to me.
So you mean so but there are also some difficulty if we want to implement the so-called maximum entropy closure. So in that closure, if you only take 2 moments, for example M0 and M1, then you can derive some analytic closure relation by maximizing the entropy. But if you go beyond 2 moments, for example, if we want to derive the moment system with 6 moments with the maximum entropy closure, then there is no analytic expression. So which means that the maximum entropy closure with the moment number beyond 2 moments, it has no analytic expression for the closure. So if you want to evolve the moment closure, then computationally, you have to solve the optimization problem in each time step and in each grid point. That is computationally unacceptable. So, yeah. So there are some limitations. Yeah. But we can definitely compare it, with the maximum entropy closure with only 2 moments. That's easy to implement. But the performance may not be good because there are only 2 moments. Yeah. Right. Okay. So let's see. Then let's in this slide, I show the performance of the higher moments. So here we compare our machine learning closure with the PN closure and the so-called filtered PN closure. So the filtered PN closure is also a popular moment closure method for the RTE. Okay, so it's trying to overcome some disadvantage for the PN closure. So that's the really rough idea. Okay, so the filtered PN closure will have a very good performance for the approximation of the M0 moment. Yeah, but for the higher order moment, as you can see in this figure, the filtered PN closure, which is denoted by FPN in the green color, it has large deviations in this figure. Okay, right. But our hyperbolic machine learning closure, it agrees quite well with the exact closure from the exact result from the kinetic model. Yeah. So this is the 7th order moment and the 9th order moment. Okay. And the next slide is I want to show you the performance of the machine learning closure in different regimes. So by different regimes, I mean I take different magnitude of the scattering coefficient. So when the scattering coefficient sigma s is as large as 100, that is the system is close to the equilibrium. So in this part, the kinetic model is very easy to do the closure because it's close to the equilibrium. And in this part, every closure has very good performance. So you can see that the radiative arrow is in the magnitude of 10 to negative 4. But when you move to the left-hand side, then you can see that when I take sigma s to be close to 1, that is 10 to the power 0, close to 1, then you can see that the p-n closure in the green dots has large deviations comparing to the machine learning closure. All right. And then I involved a model after a longer time t equal to 1. Then you can see that the non-hyperbolic closure in this long equilibrium regime will blow up. Okay, the radiative arrow can be as large as 10 to the power 6 or 10 to the power 9. But the hyperbolic closure remains stable and more accurate than the traditional closure, p-n closure. Yeah. Okay, so the next slide is about the computational cost comparison of our machine learning closure with the traditional closure. Because we have a neural network in the closure model, so then the people will ask, how about the computational cost of the machine learning closure if you taking into account of the evaluation of the neural network? Because if you want to evaluate the neural network, then you will pay some computational time, right? So here I compare our machine learning closure with n equal to 6 with the traditional p-n closure p6, p9, and up to p18. So you can see that our relative arrow for the machine learning closure is in the magnitude of 10 to negative 4. And the p-n closure, if we want to reach such a magnitude, then the model have to take up to 18 moments to reach the same level of accuracy as the machine learning model. But in this case, the computational time for the p-n closure will be 3 times as large as the machine learning closure. So which means that even taking into account of the evaluation of the neural network, our machine learning closure still has much better computational efficiency than the traditional closure. Okay, so then let me show you the conclusion. So in this talk, we propose to learning the gradient of the next higher moment. We call it the gradient-based closure. And under this framework, we propose 2 different approaches. The first one is motivated by the symmetrizer. We can preserve the diffusion limit of the kinetic model. And the second approach, we call it the eigenvalue-based hyperbolic closure. We can enforce the physical characteristic speed of the original RTE. But there are still some a lot of future work to be done. For first one is we are trying to generalize this work to the real multidimensional case. Okay, and we are trying to consider the Boltzmann equation in the rarefied gas dynamics and the Vlasov equations in the plasma physics. And also we don't know how to preserve the other properties like the rotational symmetry in the multidimensional case. And it is still an open problem to learn the boundary conditions. Okay, so these are the interesting topics to be explored in the future work. And so if you are interested in my talk, then you can see these 3 papers in the archive website. And then thank you for your attention. This is the end of my talk.
Okay, thank you very much for your talk. Are there questions? So actually, I have a question. Okay, so where is the advantage of the machine learning here? Like now, if I mean, okay, we are calling it machine learning, but if you go back,
yeah, for example, the accuracy will be better, right?
I want to go back more to the model because, okay, I mean, at the end, machine learning, what you call it machine learning, meaning that you are using previous data, right?
Yep.
So,
yep.
Right. So can you explain this a little bit more? Like, so it is okay, the term like data-driven closure, right?
Yeah.
So can you explain how this is being done? I think if you go forward, like the next, okay, here, right. So at the end of the day, what you want is 8, right?
Yeah.
The goal is to find these functions nk. So additionally, you will try to find them by some optimization. But now you want to do this using prior data. Right? So can you explain how you are using this prior data to find these functions nk?
Oh yeah, that's some details I didn't present in the talk. So the procedure is first we generate the data from the directly solving the kinetic model. Yeah, so we use some. So in this work, we use the some finite element method to solve the RTE, and from that numerical solver, we can have the data for these moments m0, m1, mn, up to mn plus 1, right? Then we can compute the derivative for the moment, for every moment. So then I can, and after I have that data, then I can minimize the difference between the left-hand side and the right-hand side. Yeah, so that's what I want to minimize. So I want to minimize the residual of this equation. So I want to minimize the residual of this equation. So basically, I want to train this neural network such that this residual is as close to the 0. That's how I do that. Yeah.
So I mean, in a sense, you start from some neural network, then you make a training. Then after you make the training, now you know this function nk, right? So then you have them stored, you have them in your computer, and then each time now you want to you want to let's say to calculate the solution, you just use your functions nk, right?
Yeah. So it is stored in my computer after it is trained. It is just some function, but it's some neural network represented by some neural network. Yeah. composed of the composition of different linear function and the nonlinear functions.
Okay. Now I want to ask another question. I mean, it is well known that this kind of closure may depend also in the regime in which you are solving. So let's say if you are solving in some limit, if you are taking a limit like a diffusion, I mean like some diffusion limit. My question is whether these functions, you learn them for a specific kind of situation, but now if you change your situation, you have to learn these functions again, right?
Yeah, that's a very good point. I think so. That's what we haven't done yet, and but I think that's a interesting question. So yeah, so sure, if you first generate the training data in this regime and then train the neural network, then we cannot expect that it will have good performance in another regime. That's true. So then what we can do is, for example, we can train the neural network in different regimes separately and then combine them together. That's one possible strategy.
I see. Okay.
Yeah, so for example, the simplest case is that we can insert the scattering coefficient into this neural network. The scattering and absorption coefficient, which is an indicator of different regimes, right? So then we can expect that the neural network will behave differently according to the magnitude of the coefficient, the scattering coefficient. I mean,
I see. Okay, thank you. Are there other questions?
Maybe I have a quick question.
Yes, sure.
It was actually related to what Professor Nader was asking. So I was wondering if data you were using for the training stage, if you add to it, like expecting that maybe that data is coming from observations from a real systems, for instance. So you might see that in some approaches they add noise to data to.
Yeah, that's a question which has been studied. Yeah, that's actually a hot topic in the scientific machine learning community. So we haven't thinking about that situation yet in our context. Yeah, but I think there are a lot of papers focusing on that issue. We only have some numerical error in our data, but it's not very large. There are only some small noise. You can take it as. Yeah.
And just the last question. I was wondering if your cost functional for the training is more sophisticated just than fitting the curve to satisfy 8. So I was wondering if maybe you were adding some other constraints, like soft constraints to guarantee that the dynamical system works as appropriate.
So I'm sorry, can you repeat the question?
Yeah, sure. So you said before that you were constructing your cost functional as the subtraction coming from 8, right? To satisfy equation 8.
Yeah,
so I was wondering if you were incorporating other type of constraints in the optimization problem you use for the training, or just this equation 8.
Well, so in the optimization, we also add some the so-called so for example, well, that's maybe some technical issue. So for example, here, if we want to make sure that these eigenvalues are distinct, then we have to put some penalty in the function we want to optimize. Yeah. And in the training, in the machine learning community, it is also usual to put some there are some technique adding to the loss function to avoid the overfitting. Yeah, I guess that's what we minimize. So besides this residual, there are also some other technical terms, yeah, in the optimization. I mean,
Thank you very much.
But it's not related to the mathematics. I mean, that's just some technique in the implementation. Yeah.
All right. Thank you.
Okay. Are there other questions? No more questions? Okay. So thank you. Thank you again for very nice talk, and thank you all for being here.
Yeah. Thank you again for your invitation.